everyone. Next speaker will be Anna Schwele. The topic will be coordination of electricity, heat, and natural gas systems accounting for network flexibility. So another super interesting topic. A few words about Anna. She received a joint MSc degree in technology and management from TUM and DTU. She's currently working towards a PhD degree at the Department of Electrical Engineering at DTU in Denmark. Her research interests include energy market, multi-energy systems, optimization, and game theory. Anna, we can see your screen, so it looks great. You can also see your camera, that's great. So can you try to, yeah, okay, we can hear you, perfect. We're ready to go. Perfect. Thank you very much.
Thanks for the introduction and hello everybody. I'm Anna from the Technical University of Denmark, and I'm going to talk about the coordination of electricity, heat and natural gas systems and the potential of network flexibility. So first of all, a higher share of renewable power penetration leads to increasing need for flexibility in the power system. And often it's the units that are at the interface with other energy systems that can provide operational flexibility. For example, gas-fired units usually compensate for uncertain wind power production thanks to their fast start and ramping capabilities. On the other side, heat pumps can provide electricity demand-side flexibility. And also combined heat and power plants, the CHP units, can provide operational flexibility by varying their power and heat output ratio. And all these units yield both physical and also economic interactions that further link and couple these energy systems to become more and more interdependent. Apart from that, gas and heat networks can also provide additional flexibility because of their ability to store energy in their networks, the so-called virtual storage. And this is because of the inertia or slower time dynamics of gas and heat flow, which can be an advantage since, unlike the power system, supply and demand do not necessarily have to be matched instantaneously. On the gas side, there's potential of storing energy in pipelines since the inflow into the pipeline is not necessarily equal to the outflow out of it. This concept is called line pack, and line pack flexibility is accumulated by making use of the available pressure differences and a higher than minimum pressure, which then results in storage of gas inside the pipelines. And line pack flexibility can operate like a buffer that is filled first and then emptied at a later time. In the district heating networks, the mass flow rates in the pipelines directly impact the time it takes for the heat to propagate throughout the pipelines, so that this time delay of heat propagation allows to temporarily decouple the heat production from the heat consumption. And especially when both mass flow rates and also inlet temperatures are control variables, this allows us to optimize the energy that can be stored in district heating pipelines. And this leads us to our research question, which is, how can we quantify the value of flexibility or the maximum potential of flexibility that the natural gas and heat networks can provide to the power system? And on top of that, how can we model this in a convex and efficient manner? So in general, it is quite complex to holistically model the multi-energy systems while incorporating the flow dynamics of each specific energy network. So most of the previous works from the literature either focused on 2 out of the 3 energy systems or neglect the dynamics in heat and gas flows using more generalized aggregate energy hub models. While we now aim at modeling all 3 systems accounting for flow dynamics and thus the network flexibility. So for that purpose, we propose a combined multi-energy dispatch, which is an ideal benchmark that assumes either one single central system operator or perfect information exchange and timing among the systems. Our core optimization aims at minimizing the total cost of operating power, heat, and natural gas systems, subject to the following constraint. On the power side, we use a simplified lossless DC power flow model, including bounds on generation and transmission. Then the natural gas flow is represented by its steady state gas flow equation, the so-called Weymouth equation. We include limits on gas supply capacity and nodal pressure bounds, and both flow and line pack are dependent on the pressure drop along a pipeline, and the flow dynamics are then embedded into the steady state model by accounting for line pack through varying in and out flows. On the heat side, we consider both mass flow rates and inlet temperatures as control variables to account for the maximum potential of the energy storage in heat pipelines. And this is based on the model that was proposed by Mithridati and Taylor, including parallel supply and return pipelines for the heating network. And we also need binary variables to model the time delays and the temperature mixing in the heat side. Then we have coupling constraints that describe the interdependencies among the three energy carriers and how the units at the interface link the three systems together. So, for example, these constraints translate the fuel consumption of gas-fired units into a time-varying nodal gas demand. Similarly, the heat production by heat pumps is translated into a time-varying nodal electricity demand. And then the power and heat outputs of CHP units are linked through an output ratio that describes the feasible operating region. Overall, our proposed combined dispatch results in a mixed integer nonlinear program. The non-convexities arise from the gas and heat flow dynamics. And since these non-convexities lead to tractability and optimality issues, we propose to use convex relaxations to model it more efficiently. So let's look at that. On the gas side, we have the Weymouth equation, which relates gas flow Q to the difference of quadratic pressures, PR, at both ends of a pipeline, using parameter K to describe flow and pipeline characteristics. And we can convexify this quadratic equality constraint into a second order cone. Similarly, on the heat side, we have the Darcy-Weisbach equation, which relates the pressure loss along a pipeline to mass flow MF with frictional loss factor L. And again, we can use second order cone relaxation. We also have linear terms for mass flow and nodal temperatures at supply and return networks, and we can relax these using McCormick envelopes. So now we end up with a mixed integer second order cone program, and we can solve this to optimality using off-the-shelf solvers. So let's look at some results from our case study, which is based on the IEEE 24 bus reliability test system and a 12-node gas system, and also a small 3-node district heating network. So here you can see the total amount of natural gas and heat that is supplied and consumed over the 24-hour time horizon. And the amount of energy stored inside the pipelines is here highlighted in the shaded areas. And it directly impacts the profiles of gas and heat supplies. So you can see that consumption and supply of gas and heat do not necessarily need to be matched in each time period. For example, here in the beginning hours of the time horizon, when wind power generation is very high, for example, heat is produced by heat pumps and then stored inside the district heating system. And at the same time, also natural gas is accumulated inside the pipelines. And then during later periods, with lower output from wind and higher demands, the line pack that was previously stored in the gas pipelines is used as a fuel, mostly for power production. And the heat that has been stored is then being consumed later. In the next graph, it shows the total cost of the integrated or multi-energy system under different levels of wind penetration. And you can see that the costs are decreasing with increasing levels of wind penetration. And we also compare the results from our model, which is here in green, to a dispatch that does not account for network flexibility, here in red. And then we can see that accounting for the flow dynamics and the network flexibility, it decreases the total system cost on average by 2% compared to the model that neglects network flexibility. On top of that, the revealed network flexibility also allows us to shift electricity production and consumption a little bit. For example, here we can see that wind curtailment is reduced when we account for network flexibility. And this effect is mainly driven by the power to heat units, the heat pumps, and it can be expected to become even more important with power to gas units, for example. Since our solutions are based on the relaxations that I've described, we need to perform an ex-post evaluation to check if the original constraints actually hold. And for the heat network, we can recover a feasible solution for the real equations. We cannot do that for the gas side. So what we did was we computed the relative error of the difference or mismatch between the left-hand and right-hand sides of the relaxed Weymouth equation for all hours and all pipelines. And here you can see that in most pipelines and most hours, there is no mismatch, but it becomes very high in specific pipelines during specific hours. And it's noteworthy that it's the pipelines that are in the loop of the network that are the ones prone to this mismatch. But since the occurrence rate of error is relatively low for our purposes, the relaxation seems sufficiently tight. So to sum up, we presented a combined power, heat, and natural gas dispatch model that accounts for heat propagation and line pack. And this is an ideal benchmark that reveals the operational flexibility of the already existing assets in multi-energy systems. And we can see that our multi-energy dispatch model reveals the maximum potential network flexibility. And at the same time, we can see that coordination of energy carriers is a relatively inexpensive solution to provide operational flexibility. For future work, it would be interesting to add, for example, multi-generation units, power to gas units, or gas-fired CHP units to increase the interactions and interdependencies among all systems even more. And it's also interesting to investigate how this potential available flexibility can be unleashed and monetized in a market context. So here you can see some of the references I had in my slides, and I want to thank you for your attention, and I'm here for any questions.
Thank you very much, Anna, for a nice presentation. Is there any question? Yeah, I can see one from Mats. Can you comment a little bit, Anna, about the solution times for different convex problems? And then if you look at the linear coupling constraints, where this, assuming constant efficiency, could have used a piecewise linear approximation, for example, given that you already had some integer variables?
Yes.
So there's different questions. Sorry, let's start.
No,
Yeah,
no,
with the
I can
solution
see it.
time. Cool.
It's three
Okay, great.
questions.
Excellent.
So,
Great.
the solution times were very fast since it's convex problems that we're solving. It's few seconds, but also it's worthy to note that our test case is not very big, and it mainly depends on the size of the district heating network, since that's where the binary variables occur. So making this bigger makes the solution time sufficiently longer. Then yeah, all our coupling constraints are linear, and we assumed constant efficiency here. And we did not use piecewise linearization, since actually we have compared, at least for the gas side, the approximation with the relaxation, and for us the relaxation was significantly faster. And also we like the idea, I mean, the linearization is always going to be an approximation, but for the relaxation there's the chance that if the relaxation is tight, we can actually recover the original solution space. Yeah.
Thank you. Yeah, no, that's pretty clear. Can I ask you, just check, there is something from Dan, or thank you for the presentation. Can you elaborate a bit on the implementation, and do you plan to release your implementation publicly?
The implementation of the model? Yeah. It's a simple mixed integer second order cone program that we coded in Python and solved using Gurobi. And I don't think we have the codes online yet, but yeah, we could easily share that online.
Okay, that's good too. There is a more general question here. It's say that County in New York has a smart users reward program for reducing gas demand. Is there anything like this in Europe? I mean,
personally, I'm not familiar with any reward programs for reducing gas demand. Yeah, I don't know. I don't have any context on this.
Yeah, not sure. Not sure either. I have a question, Anne, about the physical flexibility. How you develop this physical flexibility is like, do you particularly on power to heat, do you change significantly or do you change at all? Actually, I mean, to what extent do you change the temperatures in the heating system, basically? And then for the gas system, how do you play with the pressures from a sort of physical perspective?
Okay, so the power to heat units have constant efficiency factors, producing heat from electricity. Then the temperature, only the inlet temperatures in the district heating networks are variable, but within very limited bounds, to be honest, to keep our relaxation as tight as possible. And on the gas side, it is very similar to the model that Lucas described earlier. So we simply account for line pack with varying in and outflows of each pipelines. And then additionally, we have the restriction that the line pack is dependent on the pressure drop along a pipeline.
Okay, thank you. Can't see other questions, so I think can stop here. And thanks again, Anna, for a nice presentation, nice work.